Once again, good morning to one and all. This session will be taken by Professor Monalisa Pattnaik ma'am from NIT Rourkela on the topic Design, Development and Coordinated Control of a Wind Energy Assisted LVDC Microgrid. Professor Monalisa Pattnaik received her MTech and PhD degree from IIT Kharagpur, India in 2006 and 2013 respectively. He is currently an associate professor with the Department of Electrical Engineering, NIT Rourkela, India. Dr. Pattnaik is a recipient of the POSOCO Power System Award, Power Grid Corporation of India Limited in 2013. Her research area are power electronics converter control, renewable energy system, hybrid energy storage system for EV charging, interlinking converter control in hybrid microgrid application, electric vehicles and machine drives. Now I will invite Professor Pattnaik ma'am to deliver her lecture. This is over to you, ma'am.
Thank you, Anindya, for the introduction. Good morning, all. Today we are on the fourth day of the short-term course, that is STEM 2023, and already I think we are sticking to the schedule. And I must thank all the participants for presently hearing to us. And today I'm going to present on the topic that is design, development, and coordinated control of a wind energy assisted LVDC microgrid system. So on the fourth day already we have covered many aspects of microgrid, its operation, control, power management, the many challenging issues for PV assisted systems mainly. So that's why I thought I should give importance to this wind energy system, and I'll start my presentation having all these outlines. First I'll discuss about the why we have taken this low voltage DC microgrid application. I'll justify the reason behind it. Then I'll describe in detail about the development and the main major components of a wind energy conversion system. Then by this time, as all of you know, that when in a renewable energy aspect, what is the need of a battery storage. So I'm not going to address those details. I'll talk about how the storage is integrated with a developed wind energy conversion system. Then my focus as I'm saying, it is mainly for a laboratory setup development, where I'll talk about the real-time implementation of this wind battery assisted LVDC microgrid. This is the low voltage microgrid application specifically I'm repeating. And then it's energy management, coordinated control for this developed microgrid system, and some real-time means the experimental studies and its resultant discussions. So coming to the introduction to the microgrid, mainly the renewable energy means microgrid may have having the renewable, it may have the conventional energy sources or may not be having. So we can have only renewable energy sources, and in mind the system we have considered, we are considering a microgrid system having only renewable energy sources. And then the other components are obviously the storage, the power electronics converter, and it may be a grid or load. So as already told by many of the experts, as it can operate in a standalone or islanded or grid connected mode. So but here I'll be focusing on mainly on the islanded mode or the standalone mode of operation. So coming to the advantages, obvious advantages which the microgrid is offering, that is energy efficiency, higher reliability, reduced carbon emission, reduced per unit cost of energy. So when we are getting all this, there are some of the advantages. So the challenges we are facing are the energy management issues, the coordination with the integrating with the grid when we are operating the voltage and frequency control, and the proper power management and its coordination are the major challenges which for different case studies already it has been discussed for PV assisted systems. So here again I'm in this slide I just want to show that the system, as I am considering the microgrid is having the renewable energy sources. Here we have considered there are many options, but in Indian scenario, we have the two viable sources which are more promising in nature and complementary to each other are the PV and wind, and those are almost affordable, means at par with our conventional, the cost is almost nowadays at par with our conventional energy sources. So we have considered this PV and wind as the two renewable energy sources. Then already as a storage, what is the need of storage? It is already known to all of you. But similarly for hybrid storage or the composite storage system, we have considered the two complementary energy storage, electrochemical energy storage systems having high power density and high energy density. High power density, that is the supercapacitor, and high energy density is the battery. We have considered these two storage systems. And when we are integrating this with either standalone system or grid, so the next component which plays the major role is the power electronics converter. So based on what is the position of the means from the source, if the power electronics converter we are choosing, so if it is a PV source or if it is a wind source, so it can be the power electronics converter can be AC or means AC to DC, DC to AC, DC to DC, or if it is a grid connected system, it can be AC to AC system. So based on that, we have to choose this power electronics converter. While choosing our system requirement, we have to choose it properly. So that plays a major role, and I will be focusing mainly on this power electronics converter topologies. And and also already I have mentioned it can be a grid or a standalone load condition. So load can be a residential load or industrial load. And but in my presentation, we will be focusing for a low power application, basically the domestic loads we'll consider. So next, coming to means based on this type of source and load. So coming to the configurations of microgrid, we can have the options like if the source is both DC, means both source and load is DC or AC, so we can have the DC microgrid, AC microgrid, or combination of both. And but here I want to clarify that if it is a DC microgrid system, it doesn't mean that if my source is having AC output, I cannot connect it. That is possible. That is there plays the role of the power electronics converter. So if my source is PV itself directly, okay, there also I need a power electronics converter for extracting maximum power. Already in previous talks, already it has been explained in detail. Then comes the AC microgrid, where which is a whole power system what we are having right now. That is completely means power system is mainly based on the AC. But due to the inherent advantages what we are getting in case of this DC microgrid systems, that is no reactive power requirement, there is no phase synchronization issues, then reduced AC to DC conversion stages in case of PV based systems, and it is easily compatible with our efficient smart home equipment like LED lamps, the BLDC fans, the BLDC motor as a EV motor. So now this again from this AC system, we are again trying to move towards this DC based systems. So when we are getting some advantages, so simultaneously we have to face something, means we have to face some challenges here. So like the limitations or the challenges we are facing in this when we are again moving from the AC microgrid towards the DC microgrid are the lack of proper standard and codes, then high initial cost and investments, immature protection system for this for high voltage systems, and mainly the unfamiliarity and less of awareness. Means we are so much acquainted with these AC systems, so we are reluctant to move towards again DC. So that is the another reason. So why there is a tussle between this AC and AC system and DC system. So the first point what I have mentioned, that is the lack of proper standard code. So when we thought to develop we'll start researching on this DC microgrid part, then we searched in the literature and we found that there are standard voltage levels which are not properly, means like for AC microgrid we have proper standard codes which are for means for the distribution level we have 415 volt and 50 hertz system. It is for Indian scenario. And but in DC we don't have any proper code, but in literature we found there are two voltage levels which are below 100 volt and two are above 100, that is 100 to 400 volt, where power is between the application is up to 500 kilowatt, and another is 400 to 1500 kilowatt application where we can go up to 10 megawatt power range. So, but the applications are different. So there are applications like shipboard and aircraft and transportation systems where we can go for high power applications like up to 10 megawatt. But when the voltage level is more than 120 volt, it becomes lethal. So we need a proper protection scheme, which is means for the DC it is not yet matured. So, but when we are handling a low power system, then it is very safe, means low power at low voltage level. So we thought to we can, means we don't need a proper obviously protection is needed, but it is not so much essential. So that's why up to few kilowatt application, this that is less than 100 volt. So we thought to go for this low voltage applications, and there is a huge opportunity to create a global DC standard when, means for applications like remote areas, means in villages and where we are going to have smart home, means in future we can have the smart homes. So and in IEEE has also declared this 48 volt is a standard for rural and remote electricity applications, and it is as it is considered to be most economical from cost and performance point of view. So that's why this is the justification why we have fixed our we have chosen this low voltage DC microgrid system. So our bus voltage is fixed when we have thought to design a system, and that means a hybrid renewable energy systems, means we have hybrid sources and hybrid storage. So main objective of this work is to design and develop a LVDC microgrid with multiple renewable energy sources and multiple energy storage systems. So for this we have considered this is the system configuration where we have considered two renewable energy sources. One is the wind and another is the PV, and there is a storage, means we have multiple storage also option, means one is having high power density, that is the supercapacitor, and high energy density, that is the battery. And this part is already explained by Professor Rai and his student Anindya. Means totally the power management, its control, its implementation is clearly, and for the different power means control techniques used for efficient energy management is completely discussed by them. So I thought I should consider the system that is the wind system. And so I'll start from the scratch of this, means what is the each component of a wind energy conversion system, and then means I will consider a single renewable energy source which will be integrated to a single storage system, and then its power management and means the performance evaluation during the different case studies we'll discuss in detail. So then coming to develop the whole system, that is our main aim, but in today's lecture I will focus on these first two parts. So here if you see the total, while we are trying to develop a system, so this is divided into 5 tasks, but as I have started with I've targeted to develop the wind energy conversion system, and then we are trying to integrate the PV and then the HES. So that the flow diagram is like this, means how the for the execution or the implementation of this system, first we have designed and developed a wind energy based system in our laboratory, then it is integrated with the battery storage, and then it is the performance is evaluated by the proposed power management scheme. So these two will be I'll be focusing on today. So already this part is already mentioned, it is covered. So coming to the, then before going to the power management, the system implementation, I will focus on what is a wind energy conversion system. So coming to the main components of this wind-based system, so I'll start from the very basic, means how power is getting converted from wind to from wind energy, how we are extracting the electrical power. So as we know, wind is a very low quality energy, and when we are converting from wind to the electrical, first we need a wind rotor or the wind machine or the wind turbine we say, which is converting from the wind energy to the mechanical energy, and this wind turbine is coupled to a generator which is giving us the electrical output. In between we have the component that is called a gearbox. So this component is basically a optional one. So depending on the speed of the turbine, so we can have a gearbox here, or the turbine can be directly coupled to the generator. So basically, so what is the speed means? If I am choosing a low speed generator, then obviously I can directly couple to a wind turbine. But if my generator is a high speed one, like the induction generator, so but there obviously this gearbox is a must. So based on that, we have a different type of wind energy conversion systems. So first I told this is the wind machine or the wind turbine, then the gearbox, then the generator, then comes two components, this is the converter and the transformer. When it is it can be, here I have shown the grid, but it can be a standalone system also, it can directly feed to the load also. But this converter and transformer is also means when means during 80s or 90s when we have started extracting means using this wind energy for electrical power generation purpose. So initially it was, the system was very simple. So this converter is also not a compulsory one. So directly we can feed from the output of the generator to the grid or to the load. So this how we are choosing these components. So based on that, we have different type of wind energy conversion systems. So first is based on the operating speed. So when I'm talking about the operating speed, it is fixed speed or variable speed system. Then based on the power output, the size which we are applying, that is a small scale that is up to 10 kilowatt. Then medium scale that is up to 100 kilowatt. Then 100 kilowatt and above, we are considering it as a large scale systems. So then comes, it is already I have mentioned, it is a grid. It can operate in a grid connected or on grid and off grid mode. So then based on this, so we have different options of generators. So when we are choosing whether it is a fixed speed system or variable speed wind turbine system, and what is the, obviously both are having its own advantages and disadvantages. Fixed speed system is obviously a simple system, so which was means nowadays it is almost obsolete. Okay, fixed speed system, when I am telling it is a wind energy conversion system, and the wind is varying, the wind speed is varying, so obviously the turbine which is rotated by the wind, so cannot means it will vary, and correspondingly the coupled generator, the generator coupled it, the start speed of the generator, obviously it will vary. Then again I am saying it is a fixed speed turbine. So what is the reason? Means fixed speed with respect to the variation in speed that is we are allowing. See here the variation is very less, means within less than 2% variation. So that's why we are considering it as a fixed speed turbine, and there the generator option is only squirrel cage induction generator, which is very rugged and very simple in construction and also cheaper. So means years back in around 80s and 90s, we are going for this system where we are not using any power converters. So this is a system without power converters, so which is connected to grid. So because of this, as there is no control, so and we are directly feeding to the connecting to the grid or load, so the power will fluctuate, means depending on the variation in speed, the voltage, the grid voltage, it will affect a grid so it is not very much useful. So nowadays no one is going for going for these fixed speed systems. So compared to that fixed speed turbines, these variable speed turbines, where the power that we can capture or we can extract from this Variable speed wind turbines is comparatively more, around more than 30% we are getting here. And again, as I have told, based on the whether we are using a gear or it is a gearless system, we have two options, that is indirect drive, which is a without gear system, and direct drive, that is a gearless systems. So again, this if we'll compare both indirect drive system and direct drive systems, so both are having its own advantages and disadvantages, because when we are removing the gearbox, so obviously the system is more robust, but as well as the speed of the generator is becoming less. So speed is less means the rotor, the generator has to have more number of poles, so the size of generator as well as the size of converter is increasing. So here, when I am talking about a direct drive system, indirect drive system, so both are in use. And in direct drive, we have the options. When we are choosing a direct drive system, so we cannot go for a induction generator based system. So only option is the synchronous generator, where we have the wound rotor synchronous generator and the permanent magnet synchronous generators. So and similarly, when we are talking about a gear with gear system, that is indirect drive, where the generator is having a larger speed, means for suppose 4-pole generator, it is a 1500 rpm. If maximum we can go for an induction generator with 8 poles, so it is around 750 rpm. So with that speed, the options are we have the induction generator as well as the synchronous generator operations. So both are having the gearbox. So, but then coming to the here, I have mentioned this violet color, which is showing the full capacity power converters. When I am choosing a generator with either synchronous generator or a self-excited induction generator, which is nothing but a squirrel cage induction generator, that is in that case, the converter we have to choose here is of a fully rated, means whatever is the machine or generator rating, so same capacity we have to choose. But whereas when we are going for a wound rotor or the self slip ring induction generator, then the converter will have a reduced power rating or the low power rating generator. So why it is, that I'll explain. But again, coming to the type of, after knowing the type of generator and correspondingly what will be the converters, we'll see the what are the different converters means we can have, means the different topologies of the converters for each type of the generators. Then as I'm focusing on a low power application, I should mention here that we have for this low power nowadays the two promising options, means the generators mainly we are going for it is PMSC type with gear and without gear systems. So that is for the small scale wind turbine systems. Then already, as I have mentioned here, you can see this is a system with a DFIG, that is double output or doubly fed induction generator. I have mentioned it is a double output induction generator. So somewhere the names means these names are means anyone can use, both are acceptable actually. And as here we can get power from both stator and rotor, it is named as either double output or doubly fed. But whereas this doubly fed is more acceptable one. And here, as just before I mentioned it, here it is using a reduced power converters or partial scale power converter, because the converter is connected from the rotor end, and the rotor is handling only the slip power, not the full power. As the slip, the SPG is used here, so the converter used here is of reduced power rating. So that's why it means the cost of the system is reducing because of it. But and this system was very much useful and attractive till 2000. Now again, though we are having a means fully rated converter or the full capacity converter, but again we are switching for the system having full capacity with the permanent magnet synchronous generators, which is having providing other advantages. So specifically what I want to say is that this system what you are targeting to design, or for which application you are using and at what power level you are using, you have to choose the proper generator, then the corresponding converter topologies. So this is a system shown for a grid connected system. Then this diagram is for a standalone system where if there can be a DC load, it is directly feeding, and if it is it is feeding to a AC load, so we need another extra inverter here. So the output of the wind system or the generator is AC, means basically three-phase AC we are getting. Means and I have discussed about the generators different types. So no here I means told about the we have an option of DC generator because of its limitations, as we all know why the DC generator is not preferable for this system. So based on this as output power is AC, and then we have to obviously when we are connecting it for a DC grid, we have to choose a AC to DC converter, and this converter configuration will vary depending on our application. And as I am talking about a standalone system, so obviously to make the system more reliable and stable, so there is the importance of the battery here, and the battery will be connected to the DC bus through another converter. And here if you see the converter which is connected to the renewable energy source, here it is a wind, so this is a unidirectional one, whereas if it is a storage or it is connected to a grid, then in that case that has to be bidirectional one. So these are the differences, means we have to, so that is the main focus, means how we are going to choose the system stepwise. So then comes the converter topologies with respect to the whatever, so we have different generators already I have told. Then comes the, for a PMSC based system, so what are the possible topologies? And I'll start with the age old system, means starting from the 90s. So when we have started with a simple system, and then at that time initially the AC is converted to DC using a diode bridge rectifier, and when it is connected to a grid, it is through a thyristor based, means ACR based inverter system. And because of the obvious problems with the ACR based systems, which provide lower order harmonics, more losses, and it is the as the harmonics introduced are of the lower order, so the filtering is also difficult, and we need a active power compensator because of its poor power factor operation. So all this is, but the uh, used here was the AC to DC, means uncontrolled rectifier, diode bridge rectifier, then a thyristor fed inverter. Next is the one where instead of having directly connecting to a SCR bridge, so we need because we are using a wind energy conversion, means so we when I'll talk about the what is the need of maximum power point tracking in case of PV, all of you know from yesterday's lecture why we are going for this, but with respect to wind I'll explain just after it. So here for extracting maximum power from this wind energy system, after converting it to DC, we have introduced a chopper here, which is responsible to extract maximum power. Then instead of the thyristor based converter, it is replaced by our PWM based VSI, voltage source inverters, so which gives a higher harmonics which can be easily filtered out, and it gives improves the system performance. And so that's, so next, this is the system considered next when I'm connecting it to a grid, and when I'm stopping here for a DC grid, so I have the system, a diode bridge rectifier, a chopper, which is responsible for extracting maximum power. So these are the options. So if I am only for a DC grid I'm operating, so this is the converter involved for the wind energy conversion system. Then comes the next option for a, that is the back-to-back converter. So in place, instead of this diode bridge and the DC to DC converter, it is replaced by a control rectifier. Here it is shown as a SCR based, but nowadays we are going for a control PWM rectifier. So this SCR based system was used beforehand, but because of nowadays SCR is also obsolete one. So in both the cases we are going for this PWM based controlled rectifier and as well as the inverter. So this one, the machine side rectifier, the controlled one, is responsible for extracting maximum power, whereas the grid side, or if it is a standalone system, and the grid side converter is responsible for maintaining the grid voltage and frequency constant. So then coming to the, this is for this converter is useful for both PMSC and induction generator. The two induction generator, when I'm telling, it is a squirrel cage based system, not the DFIG based system. Then comes the topology, which is useful for our DFIG based system. And here basically already I have mentioned previously what I have discussed. If you see, this is a direct drive. Direct drive. There is no use of gearbox. So basically, we are going for a low speed generator. Then, when we are going for choosing the only option of induction generator, so the gearbox is the most. So with gear system, and here the option is when we are choosing a slip ring induction generator, or that is in the form of a DFIG. So we have the option, this is the oldest one, that is called the static Kramer drive, where we have from the rotor side, the AC to DC conversion is done by a diode bridge rectifier. Then we have the thyristor based inverter, which is connected through which it is connected to the grid. So power here, as this is a diode bridge rectifier, so we cannot have a bidirectional power flow here. So power can flow from the rotor to the grid only in case of it if it is a super synchronous operation. And here in for this case, we cannot have the bidirectional, means subsynchronous operation is not possible, means power cannot flow, means we cannot inject power from grid to the rotor. So that is the disadvantage of this system. So further, this is improved by replacing this by a controlled rectifier. So when we are replacing it by a controlled rectifier, it is called a static Stravius drive. And then in that case, we can have the power flow in both the directions. So these are the different topologies available for wind energy conversion system for different type of generators. So this is the option, means here we can see as it is connected to, already I have mentioned that this converter what we are choosing back to back one should be of partially rated or reduced power rating converters. So that is the main advantage. And here we can, with the variation of speed, we can the cost is also reduced to the variation speed where it is allowed up to 30%. The cost as well as the size is reduced up to 30%. Then comes the DFIG based system with the same thing I have shown here. With respect to that, it is replaced by a PWM rectifier or inverter, depending on in which direction power flow can be, in both the directions, depending on whether what is the speed of operation, whether it is a subsynchronous mode of operation or supersynchronous mode. If it is subsynchronous, power has to, means will be injected so that it can operate as a generator, means from grid to the rotor. And in case of supersynchronous speed, we can get power output from both rotor as well as the stator. So that is the advantage here we are getting. But again, so this is the, but this is in our system we have not considered this one. We have considered first, means parallelly in our lab we are working with taking the SEIG squirrel cage, that is a self-excited induction generator, as well as the PMSC one, and both the systems are developed parallelly. And but in today's discussion, I will be talking about the SEIG based system. So after this, the most advanced one is after this back-to-back PWM converter, we have the option of for this gear with gear system. When we have a DFIG, it can be there is the option of direct AC to AC conversion instead of AC to DC, then DC to AC. instead of two stage, there is a single stage conversion is possible by using this matrix converter. But when we are choosing this matrix converter, the complexity means control complexity is increasing a lot because it is having 3 switches per phase, so almost 9 switches, and that has to operate in bidirectionally. So almost 2 to the power 9 switching states are available, so which has to be controlled accordingly. So control complexity is really high. So that's why, though the main advantage here is we are getting rid of the bulky capacitor here, disk-link capacitor, but simultaneously there is a increased control complexity. So that's why this converter is already means in the research state, but mainly in the practical implementation we are going for this back-to-back converters. And this is the already I have explained about the when I am taking a squirrel case based system. So here it is a gear based, and instead of the partially rated, it is connected from the stator. Both the rectifier and inverter are fully rated capacities, and for all the systems I have shown in means it is connected to grid, but it can be directly means for standalone system also the line side converter will play the role to control the voltage and frequency of the system, and the machine side is responsible for extracting maximum power. So this is about the generator and the converter topologies. So for a wind energy conversion system is the mainly used. There are several more topologies also. So here if I want to summarize, so this is the summary. You can see already I have explained this. So for a fixed speed system, we can have the option of squirrel cage induction generator, whereas for variable speed systems, we have all the options of synchronous as well as induction generators. And only this DFIG based system is having the converter of partially rated, whereas others are going for a fully rated converters. So this is the summary of the generators along with the topologies of the converters for wind energy conversion systems. So again, if you will see the evolution of wind turbine size and the power electronics impact from last 40 years, starting from 1980s to here I have shown the up to 2018, but it is in the same trend. If you will see up to 1990s, so the if you will see the how the turbine size gradually increasing along with the power handling capacity. So it increases from 50 kilowatt to 10 megawatt, whereas the corresponding the turbine diameter increases means from starting from 15 meters to it has reached to more than 200 meters by now. So it is given up to 190 meter, but we have more than 10 megawatt capacity also. And correspondingly, if you see the interference of the converter, so first as to make the system simpler, we have started with a fixed speed system. So there is no power electronics converter. In between, then we have a converter that is the for a variable speed operation, which is nowadays these two are almost obsolete. So which is used for the DFIG or the wound rotor induction generator. Then and the till 2000 this DFIG based systems is getting more attention. Again we are going for this fully means the generators with induction generators as well as permanent magnet synchronous generators having fully rated, and then it can be with gear system or it is a gearless system or with gear system. Then that depends on which area or which application you are going to use. So this is the options of the generators. So this is the overall idea from the what I have discussed just now, that is the wind turbine size and the sorry, wind turbines and with respect to turbines, what is the generator type and the corresponding power electronics converter topologies and its size. So then comes when I am talking about this wind turbine, I am talking about this maximum power point tracking. So wind speed varies. So how the power that is available from wind, how much we can extract. So power available in wind is half rho AVQ. Whereas how much we can extract, if you see the theoretical limit, it is maximum up to less than 60%. That is called as 59.3%. That is called base limit. So it is less than 60%. That is the theoretical limit. And when means practically when I'll implement, I can extract maximum 35 to 45, or max to max it can go up to 50%. So in that case, and if you see the output power, that is the mechanical power output from the wind turbine, is proportional to the cube of the wind velocity, and the curve is like this. So if you see, so this curve, power curve will confirm why there is a need to operate at maximum power points. So because of for each wind speed, if you see in this power curve, means power versus wind speed, means for each wind speed there will be getting a for a particular rotor speed. If you plot the curve varies like this, and so there is a optimum turbine speed at which we can extract the maximum power. So that is the need why we have to extract maximum power, and there the power electronics converter plays the main role. So then this is after knowing these characteristics, so then further if we see what is the operating region. So as just now I told, power varies with cube of the wind speed. That means if wind speed is very high, so we can extract more power. So we'll be very happy, okay, we can get more power. But if wind speed is below certain value also, though the turbine blades are rotating, then net output after supplying the system losses, the output at the generator is almost, we cannot supply to the external load. So in that case, so we have, there is a operating limit. So if the wind speed is below certain value, so which is known as the cut-in wind speed, so we have to stop the turbine. Then similarly, if wind speed is very high, so though power available is means a lot of power is available, but because of the physical constant, we cannot allow the turbine to rotate further, because it may damage the whole system. That is during the storm or cyclonic condition. So at that time we have to stop the turbine. So that speed limit is called the cutout speed, or cutout speed, or the falling speed. So if the wind speed is below cut-in, or if it is greater than cutout or falling wind speed, we have to put the turbine in the parking mode by putting some external brake, mechanical brake here. Then if the wind speed and what is the rated speed? The rated speed is the speed at which the generator can give the rated output power for a particular location. So if the wind speed is between the cut-in to rated, then within that region we can operate at this point. So we will be able to track this maximum power point by doing the generator control. So that is if the wind speed is between the cut-in to rated, so we'll go for the MPPT operation. So that is the region 1 operation. Then comes if the generator limit has reached, so we have excess power. We have to, obviously we cannot overload the generator, means we cannot extract more power than its rated limit. So obviously we have to limit the power by applying some control mechanism. So there we cannot apply generator control, we have to go for the turbine control. So there that is the mechanical control or turbine control, where we are going for this stall control mechanism or pitch control mechanism. In stall control we have passive stall control, active stall control. I am not going to those details. Just you know that we have two operating zones. One is the MPPT zone, another is the power regulation or the turbine control zone, where we are going for either pitch control or active stall control nowadays. And pitch control compared to active stall control, pitch control is more popular. So what is pitch control basically here? So if you see in the CP lambda curve of the wind turbine, if you see the CP for various values of pitch angle, with we are getting maximum power for beta 0 when the pitch angle is minimum. And by increasing with the increase of pitch angle, the power is reducing. So this thing can be used to control the pitch. Means if you increase the pitch angle, so there will be no interaction with the turbine, means with the wind. So there will be output power will be less. So in that case, we can use this control mechanism to limit the power. So that I will explain while showing the implementation of our system. So we'll just remember that we have two regions. One is MPPT control region, another is the generator protection zone. That is where we are using the pitch control mechanism. So with this, this talks about our uh, whole means wind energy conversion system basics. So then we have thought to how to when we are going for the design. So this is the system first. Already as this part is already explained by my student Pradimna, he explained in detail about the what is the need of this wind turbine emulator, because when I am talking about a basically system how to develop in a laboratory. So and physically we cannot install a turbine here. So we are going for a wind turbine emulator which will emulate the characteristics of a practical wind turbine. And here we have taken a DC motor based system, because in a machine lab if you find we can have this DC motor generator set or motor generator set are easily available. And when I'm talking about a motor generator set, the options are obviously DC motor. We can have induction motor or permanent magnet synchronous motors. So with all the type of motors we can emulate the turbine characteristics. But here because of the simplicity and availability we have taken a DC motor based system. And this part I am not going to explain because this is already with the implementation part. He has explained clearly the wind turbine part. Then comes the design of the system. When I'm talking about the design, so here we'll start with the choice of generator, already I have mentioned. Then comes the choice of suitable converter, which is required to extract maximum power from the wind system. So first we'll choose a generator for that at what power level we are working. After that, we have to choose a proper converter for that to extract maximum power. And then this we have to implement this MPPT algorithm with the wind-based system. So this is about the complete wind system when we are developing. Will do. And then after developing the wind system and checking the MPPT algorithm, its performance, how whether it is working properly or not, whether it is tracking the MPPT is tracking with the variation of wind speed, with variation of load or not, then we'll try to integrate it with a battery storage system, because of if we have depending on our sub means the load demand, whether we have excess of wind energy generation, then we can store with a storage means battery. Here we have considered the simplest one, and uh, the single storage system. And then we need to, because of previously with without battery, the with the variation of wind speed the bus voltage was not fixed, it was fluctuating. So we have to regulate the DC bus voltage. And then comes the power management. So these are the steps we'll see step by step. So for that, for the system what we have means considered here, so already this part is completed. So these systems we have first developed with a ACIG based system, self-excited induction generator we have considered here. Then the then as already this I have mentioned, the bus voltage we have fixed at 48 volt. So based on this, we have chosen a buck converter, and for simplicity, we have taken a diode bridge rectifier, and then a buck converter, which is responsible to extract maximum power. So, so this forms the wind energy system, and its implementation is done first. Then it is interfaced with the battery through a bidirectional converter. So which is the simplest means configuration. So before going to the final implementation part, I'll show this is the specification of the motor generator set we have considered. And for this buck converter, it is a standard design procedure where the filter parameters are calculated. And the switch we have taken it as it is a for low power application, we have considered it as a MOSFET here. And it is operating at the switching frequency is 10 kilohertz. Then the MPPT algorithm is implemented here. First, we have tried with the normal conventional P&O MPPT algorithm, which was described in very detail in the yesterday's class by Professor Samantha. So here first, after implementing the basic P&O algorithm, then we have tried to modify the same concept what Samantha sir has explained about the drift phenomena, because when there is a that was the case with the PV-based system, but here also we thought to see that whether with the wind speed variation something is happening or not. Yes, there was, when there is an increase in wind speed, there was a direction mislead. So the algorithm fails to identify the correct direction. So the drift phenomena is avoided by introducing a current loop in this algorithm. So then the algorithm is modified and further tested. So, and also means it is mathematically verified the similar characteristics. When there is an increase in wind speed, the current is also positive. So that's why this loop of what we have discussed for the PV-based system, same theory means fits here also. So that is with that thing we have published a paper in IEEE transaction and power electronics with the same concept, but applied to a wind energy conversion system, because when we are talking about this wind energy conversion system and its with respect to the PV-based system, the complexity increases, means it's quite large. And when we are talking about this, how to tune this MPPT algorithm, how to choose the sampling time, means the MPPT perturbation time, those things in the next session it will be explained by my student, another student, Balaji. So he will be talking about how to implement MPPT algorithms in the wind-based system. So I'm just skipping this part, that here in this work we have improved our algorithm, means the performance of the MPPT algorithm by modifying the algorithm, and that will be supported by some experimental results. So then coming to the after developing this wind energy system, so we have tested that we are able to extract maximum power, but the burst voltage is obviously, when we are checking by varying the wind speed, the burst voltage is varying, fluctuating. So which is not at all desirable, and also when there is more power and we have less demand, so we cannot store it. So we have tried to integrate that with a battery storage system. Initially we have considered this single one, means one storage only, and here DC, as this is we are considering for a DC bus, so the options are non-isolated and isolated, and we have considered the simplest one, that is the non-isolated half-bridge bidirectional converter, so which can act as a source or load depending on your power generation from the wind side. So the generator means the design of this system is very means conventional one. This is a simple topology we have taken first, and here after designing this filter components for this bidirectional converter, we have tried to regulate the DC bus voltage by designing the this voltage and means dual loop controller. So where the outer loop regulates the DC bus voltage and the inner loop regulates the charging discharging current of the battery. Then that is the basic work we have, means initially when we are starting to implement this part, we have checked the performance of the battery in a normal scenario, that is in a safe operating, that is the SOC of the battery is within the safe operating region. That is, we have considered here 50 to 90%. The SOC is within the safe operating region. So this actually, this lower or upper limit is defined, means that it can be 30 also, but we have considered 50% here. So we have tested the system with this SOC, and this figure shows that this is the complete diagram of the system developed in our lab. Means photograph here it is the DC motor coupled with the ACIG. Then this is the excitation capacitor, and this system already you have seen in practical case. Pradyumna has already shown you in detail. So then coming to the after testing the basic performance, we thought to implement the power management scheme, where so in case of this wind power generated after supplying the substituting the losses in the system. So available power will be fed to the load, and depending on the whether wind power is more or less, the battery will be either charged or discharged. So in the initial case, we have tested the system performance with variation of wind speed and variation of load. Then other case studies are also considered that I will be explaining also. So the after so I'll show you the. So this is the proposed power management scheme where initially we are talking about this. I'm talking about this MPPT, means the generator, means we are extracting wind. Wind power and it is operating in the MPPT control mode, and the BDC is operating, means regulating the DC bus voltage. So here the BDC with the output of the BDC controller gives the battery reference current, and in case the battery is charged fully, then the controller will generate the switch to the zero reference current, that is battery will stay idle, means it cannot charge or discharge further. So in that case, so when we have tried to see the results, the performance of the system, that is the normal operating under the normal operating scenario, that is SOC is within the limit. So with the variation of wind speed and with the variation first, this result shows the during the variation of wind speed. So wind speed is varied from 6.5 to 7 meter per second. Then it is varying to 6 meter per second. Again it is reduced, and there is a condition shown that there is no wind. So in all the cases the load is maintained constant, means the load requirement is 104 watt, whereas the generation, so in the up to in the first case at 6.5 meter per second, when the generation is more around 150 watt, so the excess power is taken by the battery. So battery is charging. So if you see the corresponding charging current, and similarly with the different speed scenarios, the if wind power is more, the battery is charging with a more volume, higher current, and further if there is no wind condition, in case of the no wind here, so the battery is supplying fully to the load. The battery is discharging. So accordingly, you can see the charging and discharging nature with the corresponding SOC of the battery waveform. So this is about the normal operating condition with only wind speed variation. Then we have also tried to see this case with the load variation and as well as the wind speed variation. With the load variation, if you see when there is a decrease in load, so the battery is charging with a more negative current, so battery power is more here, battery is storing more. And for all these both the cases, previous case also the DC bus voltage is maintained constant at 48 volt, and here is the same case. But the problem arises when we are going okay, so let me first talk about the mode 2 operation. When we are going for a generator protection mode, means when I'm talking about a generator protection, first talking in the in this flow diagram, if you see first, when it will check that okay, the wind power is greater than rated or not. If it is greater than rated, then we should activate the pitch control mode. So pitch control means here from the MPPT mode, it will switch to pitch control mode. So as already I have mentioned, in the pitch control mode, here the directly it is shown the power is limited to the its rated value. Here it is taken as for 7.5 meter per second, it is limited to 170 watt. And in this case the DC bus voltage still, because the SOC is within the rated, means in the safe operating region, so the battery is storing with a constant current, and the SOC is showing it is charging. So this is the generator protection mode is activated, means So here in this case, the switch there is a switching from 1 to 2. So in the controller, how we are doing this means we have to increase the beta angle. So the controller will identify if the wind speed is more than this, so beta will increase and it will limit the power to its rated value. So that is the main condition here. We have implemented that pitch control means by increasing the pitch angle we are limiting the power. So because this is here direct turbine control is not possible in the laboratory setup. So this is about the protection mode. Then comes the battery protection, means when the battery is charged either to its higher means upper limit or to the lower limit. In both the cases, both the scenarios, what happens? Just a minute. In both the scenarios, when the SOC is reached 90%, means first the upper limit I am showing the results. So in this case, the scenario what is happening, the wind is generating, it is maximum power point it is extracting, and the battery as the wind power the compared to the load requirement battery is charging. And what here what happens, the battery as it is charged, so battery the controller will identify okay the battery is fully charged, so it will generate from the it will switch from this IB ref to it will generate the zero reference current, so battery will remain idle. But what will happen, but as battery is disconnected means we are not operating the bidirectional converter to regulate the DC bus. So at that time, but the maximum power is extracted, but what will happen, though the point will shift, now it will not extract the maximum power, but there is nothing, the buck converter or the converter which is responsible to extract power is operating the MPPT mode. So the VDC regulation is not possible in this case. You can see here the DC bus voltage, because the power is extra, there is a swell in the DC bus voltage, so we are unable to regulate. And same is the case when it is reaching the lower limit. There is a dip in DC bus voltage because the battery current is zero, battery power is zero. We are stopping the bidirectional converter, but the DC bus regulation is not possible. So to address this issue, further we have introduced off MPPT controller in this part. So where we have introduced a off MPPT controller, which is means here instead of buck converter, the bidirectional converter is stopped or it is remaining idle, but the buck converter which is extracting maximum power is now will be responsible to regulate the DC bus voltage. So that is another contribution we have done here. So for that, to implement that controller, this is the block diagram of the off MPPT controller, where the buck converter, instead of the MPPT mode, it will switch to the off MPPT mode or the reduced power mode control, where the DC bus is controlled, means the buck converter is controlled in a closed loop manner to regulate the DC bus voltage. So that is the thing we have added here in the control mechanism, and then the system is again tested for to means to addressing the issue of means during of means when battery is disconnected, we should be able to capable of regulating the DC bus voltage. And here for this case, we have tried to regulate the DC bus voltage by doing means switching from MPPT to off MPPT controller, and the switching, as if you'll see, when it is reaching the upper limit, here we have seen the controller will switch from off MPPT to off MPPT mode, and here the DC bus is regulated by the same buck converter, and we can see it is tracking the DC bus voltage very nicely. And but simultaneously the battery is generating the same zero reference current which is tracked by the actual current. So battery is protected as well as we are able to maintain the DC bus voltage. So this is about means this is in the first case when it is reaching the upper limit. Same is also done for the second case when it is reaching the lower limit. But in this case, one additional thing we have to do here, because the wind generation is less here. So after the battery controller is off, our buck converter is regulating the DC bus voltage. Simultaneously, we have to curtail the load. Means load setting need to be done. Otherwise, the power whatever is generated is not sufficient to supply to the load, because now battery cannot supply as it is fully reaching the lower limit. So in this case, load shedding as well as this DC bus which is we have tried to maintain with the help of the buck converter is done, which is clearly means the switching from one mode to other is clearly means seamless, and the transition is very nicely done here. So this is this work is also published in IEEE Systems Journal. And so with this I want to conclude, means here whatever we have seen in the MPPT part, we have contributed by improving the MPPT means the performance of the MPPT by removing the drift mechanism. Then comes the protection of, along with the normal mode operation, we have added the protection of the generator as well as the protection of the battery, and along with the VDC regulation and the overall power management and seamless operation. So this is the conclusion of this work, and it is already published. Those who are interested for this work, they can refer this journal, which is published in IEEE Systems Journal last year only. So apart from this work, so already these things I have mentioned, what are the main contributions and uniqueness of this work. So apart from this, we have these are the main publications from this work, and these are the references. So just I want to show a little bit more about my what the other works we are continuing. So as already I mentioned, we are parallelly in the process of already the PV based system is already developed with a very low, from the low power to we have reached up to 1 kilowatt, 1.5 kilowatt system. Then this is the wind PV battery based system with a single storage, and also we are in the process of integrating the hybrid energy storage system. And this is the system that will be explained in the next session by Balaji. This is a PMSC based system, and here how the MPPT for the wind energy conversion system is implemented, that will be explained by him in detail. So these are the specification of that. And this is another project we are handling where this is also a low power system, but it is here we'll try to connect it to the load. Myself and the other two coordinators are also involved in this work. So this is a DST sponsored project. And with this, I want to conclude here. Thank you all. Any questions?
We would like to extend our heartfelt thanks to Professor Monalisa Pattnaik ma'am for her amazing lecture and discussion on wind energy conversion system and power management scheme in a 48-volt LVDC microgrid. We truly appreciate you and your effort to make us understand regarding this topic. Thank you so much, ma'am. The afternoon session will start at 3 p.m. Thank you everyone.